Welcome back to the Explainer. All right, let's just dive right into this. So, if you've been following along on our journey through the auditory system, you know we've spent a ton of time looking at the sheer physical biology of hearing. Specifically, how the basilar membrane mechanically separates out different sound frequencies. But today we're shifting gears. We're moving away from the wet biology and stepping into the really fascinating realm of behavioral psychophysical measurements. I mean, think about it. How do we actually measure human hearing and figure out the precise shape of our internal auditory filters without, performing invasive surgery? Well, that is exactly what we're going to unpack today, using some incredibly clever behavioral tests.
So, here's our quick roadmap for today. We're going to start with section 5.4.1, masking and psychophysical tuning curves. Then we'll move right into 5.4.2, the notched noise technique, check out 5.4.3, variation with center frequency, and finally wrap up with 5.4.4, excitation patterns.
Okay, so the fundamental question driving this whole thing is this. What are the perceptual consequences of frequency selectivity? Right, because we know the basilar membrane acts kind of like a series of bandpass filters, separating out all those different frequencies. But how does that mechanical filtering actually translate into the rich, complex world of sounds that you and I perceive every single day? Let's find out.
All right, kicking things off with our first section, 5.4.1, masking and psychophysical tuning curves. So this is literally the very first methodological tool scientists use to map out our auditory perception. And to wrap our heads around this, let's look at the concept of hearing out a sound. Imagine I play you a band of noise, right? And it only contains frequencies between 1,000 and 1,200 hertz. Now, if I add a pure tone to that mix at 2,000 hertz, you are going to easily hear that tone, even if it's way quieter than the noise. Why? Well, because the tone and the noise are exciting totally different places on your basilar membrane. And here's the kicker. If I change that pure tone to 1,100 hertz, basically right smack in the middle of our noise band, it gets completely lost. You wouldn't hear it at all.
And that hearing out phenomenon brings us directly to the formal definition of masking. Masking happens whenever the activity produced on the basilar membrane by one sound, which we call the masker, obscures the activity produced by the sound you're actually trying to hear, which is the signal. Honestly, it all comes down to real estate in the ear. If the masker and the signal are, say, really far apart in frequency, well, that masker needs to be incredibly loud to hide the signal. But if they're close together, if they're actively competing for the exact same spot on the basilar membrane, in that case, a masker only needs to be a tiny bit louder to completely obscure your signal.
So how do we actually use this masking trick to map an auditory filter? Well, we measure what's called a psychophysical tuning curve, and it's this beautifully elegant step-by-step behavioral technique. First up, we fix a pure tone signal at a super low level, just 10 decibels above the listener's absolute threshold. Next, we introduce a masker at a specific frequency. Then, we just gradually bump up the volume of that masker until the listener finally says, "Nope, I can no longer hear the signal." And then, we just repeat that whole entire process for a bunch of different masker frequencies.
And the result of all that testing forms this very distinct V shape that you're seeing here. These curves track the exact level of the masker needed to hide a 4,000 hertz signal. See how when the masker is far away from 4,000 hertz, it has to be really, really loud to mask the signal. But when it's super close to 4,000 hertz, right down there at the tip of the V, it barely needs to be loud at all. And notice how as the sound level increases, like moving from those filled diamonds at the bottom up to the open squares at the top, the curve gets way broader. That means we're losing frequency selectivity. Oh, and here is the really fascinating part. The tip of the curve actually shifts downward in frequency at those higher levels, which absolutely perfectly mirrors the physical tuning curves we can measure directly on the basilar membrane. How cool is that?
Moving right along, let's get into section 5.4.2, the notched noise technique. Now, the tuning curve experiment we just talked about is great, for sure, but scientists wanted an even more bulletproof way to estimate the exact shape of our auditory filters. Enter Roy Patterson's wildly popular 1976 experimental setup. Instead of just using one masker, Patterson used two bands of noise. He put one above the signal's frequency and one below it. This creates this awesome little quiet gap in the middle, a spectral notch, where the pure tone signal can just sit undisturbed.
Take a look at this. Notice the pure tone signal right there in the middle, represented by that vertical line, just sitting comfortably in the white gap between the two gray noise bands. Now that black curve, that represents the listener's auditory filter. The absolute genius of this experiment is varying the width of that white gap, because as that spectral notch widens, less and less of the gray noise actually falls inside the auditory filter. And with less noise passing through the filter, the pure tone signal becomes so much easier for the listener to detect. By measuring the exact moment the signal is detected as we widen that gap, we can mathematically calculate the precise shape of that black curve.
All right, next up is section 5.4.3, variation with center frequency.
Okay, so now that we have a super reliable way to map these filters, how in the world do we standardize the math across the hundreds of different filters inside our ear? Well, the answer is the equivalent rectangular bandwidth, or ERB. See, auditory filters have these really complex swooping curves that honestly just a headache to compare. So scientists use the ERB to simplify the whole shebang. And the ERB is exactly what it sounds like. You take that messy auditory filter and you calculate a perfect rectangle that has the exact same peak output and the exact same area under the curve. It gives us this beautiful, standardized unit of measurement derived straight from those notched noise experiments.
Using these experiments, researchers Glasberg and Moore actually developed this specific formula back in 1990 to estimate the ERB for any given center frequency, which is what the FC stands for in the equation there. Now, don't worry too much about the specific numbers. What you really need to take away from this math is that for frequencies above 1,000 Hz, the bandwidth of the filter is roughly proportional to its center frequency, sitting at a pretty constant ratio of about 11%. So basically, our high-frequency filters are wider in absolute terms than our low-frequency filters. Simple as that.
But here is a absolutely crucial detail. How we actually deliver the masker and the signal completely changes these results. Historically, these measurements used what's called simultaneous masking, meaning the noise and the tone play at the exact same time. But physically overlapping those sounds on the basilar membrane actually causes the masker to organically suppress the signal, and that makes the measured filter look way broader than it really is. However, if we switch it up and use forward masking, where the masker plays then completely stops and then the signal plays immediately after, there is zero physical overlap on the membrane. And without that suppression, forward masking reveals that our auditory filters are actually much sharper at low levels than we previously thought. We're talking high-frequency ERBs potentially as small as 5%. That's a real game changer.
And that brings us to our final section, 5.4.4, excitation patterns.
Okay, let's zoom all the way out now. We've talked a ton about single, isolated filters. But how do they all actually work together as a team? We know the cochlea acts as this giant bank of hundreds of overlapping bandpass filters. So to understand how an entire complex sound is represented in the ear, we plot what's known as an excitation pattern. This is basically a visualization that shows the simultaneous output of every single auditory filter across the entire cochlea, all arranged neatly by their center frequencies.
I want you to consider this really profound observation straight from the source material. The excitation pattern is the auditory system's version of the spectrum. Let that sink in. It perfectly shows the degree to which different frequency components in the messy, complex sounds of our environment are resolved by our very biology. Your brain isn't just passively hearing noise, it is actively reading an internal biological spectrogram generated right there on the basilar membrane.
Which leaves us with this final, incredibly thought-provoking question. We've seen how behavioral psychophysical experiments, stuff like tuning curves and the notch noise technique, prove that our ears act as these incredibly precise overlapping filters. But when you're walking down a busy city street or, listening to a symphony, you aren't just hearing pure tones and white noise in a lab. You are hearing a massive, overlapping wave of complex information. So how do these internal spectrum representations, these excitation patterns, actually allow us to continuously separate the piccolo from the double bass in real time? Just think about the sheer computational power required for your brain to instantly decode that pattern. It's mind-blowing. We're going to explore exactly how the brain processes these complex behavioral listening scenarios in future explainers. Thanks so much for joining me today, and as always, keep questioning how you hear the world.